Hi guys, welcome to lesson 7.4 on evaluating logarithms and graphing logarithmic functions. The first thing that you'll notice when we start here is this is a brand new term for you. Many of you have never even seen the word logarithms before. And so when we start talking about some of these exponential functions like exponential growth and decay, sometimes we were trying to solve for a certain value, and so unfortunately there wasn't a good way to do that. So we kind of have to guess and check. Like for example, the function where we talked about the television was depreciating at 21%, and we wanted, or 28% per year. We wanted to find out how long is it going to take for the television to be worth $300. We can do that exact same example with a logarithm much easier than graphing the two functions and finding where they intersect. So we're going to be introducing this idea of a logarithm. Again, there's a lot in this lesson, so probably a lot of pausing and rewinding and making sure you kind of get the idea here, because this is a pretty tough lesson. And so again, I want to make sure that you guys are kind of getting all of this. But anyway, let's talk a little bit about a logarithm. It says a logarithm of y with a base b. So a logarithm denoted by log base b of y. And again, we call this our b. This is our base, so it's log base b of y, and defined by log base b of y is equal to x if and only if b to the x power is equal to y, given that b and y are both positive numbers and b is not equal to 1. Now, again, b can't be equal to 1 because if the base is 1, this isn't a very exciting function, because 1 to any power of x is going to be 1, even 0 there, negatives and positives. So again, b can't be equal to 0, and this is the same idea as our base from before when we talked about our exponential growth functions. The big thing is when I look at log base b of x is equal to, of y rather, log base b of y is equal to x, what I'm really saying is that b to the x power is equal to y. So if I say log base b of y, I'm saying this base to what power is going to give me this number y. Now, you're going to get much more comfortable with this, but again, the b is my base. That's the base that I'm raising to the power. And so b to this number here is my x. That's my variable. Is going to be equal to y. We're going to use this with some constants, and then we'll actually be taking a look at some of these logarithmic functions here shortly. The common logarithm is based on the most common unit of counting in our system of numbers. And since our system of numbers is based on the number 10, every time we increase by a power of 10, like 10 to the second, 10 to the third, 10 to the fourth, we're increasing a place value. And so the common logarithm is with a base 10. So if you just see log of, say, 5, for example, we're assuming that that's base 10 because we're not giving a number there. Now, if it's anything else, like, for example, log base 7 of 5, that says 7 to what power is equal to 5. Again, that's not a very pretty answer, but the bottom line is that unless we give a base, we're assuming that it's base 10 because it's a common logarithm. Now, from last section, we talked about this idea of e, where e was the natural base, and so the natural logarithm is going to use the natural base. And so that would be the log base e of some number y is equal to x. Now, from a notation perspective, instead of saying log base e, because we already have a common logarithm with the base of 10, I know that says a 10 underneath there, by the way, because we use base 10 for a common logarithm, and otherwise we use that base right there, instead of using this notation here, we use the natural logarithm notation. And so natural logarithm is ln. Again, natural log would be the other way around. But when you see ln, assume that it's log base e. So natural log of y equals x really means e to the x power is equal to y. And we'll take a look at that in just a second here when we get into natural logs just a little bit more. Okay? So, again, big thing here, common logarithm is, whoops, sorry about that. Common logarithm right here is a base 10, and natural logarithm is a base of e. And remember, e is that constant number that we talked about from last section, all right? That irrational, non-repeating, non-terminating decimal. All right, so let's take a look at some common logarithms with a base b. let's slide over to here. It says let b and y be positive numbers where b is not equal to 1. The logarithm of y with base b is denoted by log base b of y. And again, we read this, log base b of y is defined as follows. Log base b of y is equal to x if and only if b to the x power is equal to y. Again, the expression log bottom number b is read log base b of y. Log base b of y. So we're taking the logarithm of the number y with a base of b. All right, so we're going to write some of these. We're going to kind of change back and forth between logarithmic form and exponential form. Again, the logarithmic form says 2 to the 5th power is equal to 32. My base is 2. The exponent I have to raise that to is 5. So the log base 2 of 32 is 5 because 2 to the 5th power is 32. All right. Log base 7 of 1 is equal to 0 because 7 to the 0 power is 1. 13 to the 1st power is 13. And the last one's a little bit tricky. But again, your base is 1/2 being raised. Again, 1/2 to the negative 1 power is equal to 2 because, remember, negative 1 power says this is 1 to the negative 1 over 2 to the negative 1. 1 to the negative 1 becomes 1 to the 1st on the bottom. 2 to the negative 1 becomes 2 on top, and therefore you get 2. So kind of had to go a little bit of a roundabout way to get there, but 1/2 to the negative 1 power effectively just takes the inverse of that logarithm. All right, so let's try a couple on your own. Again, we're just kind of trying to get the hang of that notation. So why don't you give these a couple of shots. All right, the first one, your base is 18, so it's 18 as your base, raised to the 0 power is equal to 1. And is that true? Well, of course, anything to the 0 power is 1. Our next example is 2 to the 6th power is equal to 64. And so the log base 2 of 64 is 6 because 2 to the 6th is 64. So let's go ahead and evaluate a couple of logarithms here. We're going to have to do some simplifying as we go here because we need to try to get these things in powers such that they're representative of this number here in the base. All right, so to help you find the value of log base b of y, ask yourself what power of b gives you y? So again, 3 to what power is equal to 81? All right, well, in our case, 3 to the 4th power is equal to 81, so log base 3 of 81 is 4, because 3 to the 4th is 81. 4 to what power gives you 0.25? Well, remember, 0.25 is the same thing as 1/4, and you can see that basically if I just take 4 to the negative 1 power, 4 to the negative 1 power would make it 1/4, which is 0.25. So that says that the log base 4 of 0.25 is negative 1. All right. Next one's a little bit tricky here. This is 1/4 to what power is going to give me positive 256. Once again, this is pretty tricky here, but again, 1/4 to a power is going to give me 256. If this number is positive, then I'm going to continue raising 4 to a positive number. This is going to get smaller and smaller and smaller. So one thing is, I know for sure, is that power has to be negative, so that way I get 4 over 1. And then 4 to what power gives me 256? Well, 4 to the 2nd power is 16, 4 to the 3rd is 64, and I know that 4 to the 4th power is 256. So that means 1/4 to the negative 4 power is going to give me 256. 1/4 to the negative 4 is 256. So log base 1/4 is equal to log base 1/4 of 256 equals negative 4 because 1/4 to the negative 4 becomes 1/4 to the negative 4, which is 4 over 1 to the positive 4, which is 4 to the 4th, which is 256 over 1. Okay? And then the last one's, again, a little bit tricky, but it says 49 to what power gives you 7? Well, it has to be to the 1/2 power because I know the square root of 49 is 7. So 49 to the 1/2 is 7, so log base 49 of 7 is 1/2. All right? Why don't you guys try 2 more checkpoint problems here, and we'll be right back with solutions for you. All right, in our next example now, we want to know 1/3, helps to choose the pen here, I want to know 1/3 to what power is going to give me 9? Well, first of all, I need to flip this thing over to make it 3 over 1, and then 3 over 1 squared becomes 9. So that means this has to be a negative 2 power because 1/3 to the negative 2 makes it 3 over 1 to the positive 2, and 3 squared is 9. So the log base 1/3 of 9 is equal to negative 2 because 1/3 to the negative 2 is equal to 9. And I'll just put BC for because. Again, you don't have to write that because statement, but it is helpful. This next one says 16 to what power is equal to 4? Now you might think this is 2, right? We might be tempted to think this is 2, but 16 squared is not 4. 16 squared is 256, so that's not going to do it for us. Instead, if we think, well, 16, if I take the square root of 16, I get 4, and the square root is the same thing as the 1/2 power. So that means 16 to the 1/2 is equal to 4. So the log base 16 of 4 becomes 1/2 because 16 to the 1/2 is equal to 4. All right? So let's take a look at some examples using inverse properties. This first example here, because this is the common log, once again, we are assuming that this is base 10 like we talked about before, because if we don't put a base in there, we get to assume it's base 10. So since the base is 10 here, we're raising that to the log base 10 of 6.7. This simply becomes 6.7 because this number and the base match. So 10 times the log of log base 10, all of this basically cancels itself out and you get 6.7. Now, in the next example, we want to express 16 as a power with a base of 2 because my base is 2. So really, this is log base 2 of, and 16 is the same thing as 2 to the 4th, then to the x. All right? So if I split this 16 and take the x out here, just kind of pull the x power out over here, and then write 16 as 2 to the 4th power, because 2 to the 4th is equal to 16. Now, our power of a power property tells me that this is log base 2 of 2 to the 4x power. Well, if I'm using my notation then, this is some number over here. 2 to what power becomes 2 to the 4x? Well, 2 to what power gets 2 to the 4x? Well, it has to be 4x. All right? Since this base and this base match, effectively they just all do this, and my answer is 4x. Is another way you can think about that. Again, that's only if the base and if the base matches in the logarithm as well as the base that I'm able to write 16 as a product of 2. All right, so let's talk a little bit about inverse functions. When we do inverse functions, remember from chapter 6, when we talked about finding the inverse of a function, effectively what we did is we said, look, replace x and y, switch those two around, and solve. All right? So before I do that, I want to write this guy right here. I want to write that as exponent notation. So my base is 3/2, so this is 3 over 2 raised to the y power is equal to x. Now, to find the inverse of a function, remember, we interchange the x and the y, and then we solve for y. Well, when I interchange the x and the y, this becomes 3 over 2 to the x is equal to y. And so from the definition of the log, y equals log base 3/2 of x is basically going to give us y equals 3/2 to the x power. All right? Now again, keep in mind, we switch the x and the y around. And so what we're saying now is the inverse of log base 3/2 of x equals y. The inverse of that is the exponential growth function y equals 3/2 as my base to the x power. All right? So what we're saying then is a logarithm graph is going to be the inverse of an exponential growth graph, which should make a lot of sense because, again, logarithms undo raising things to powers. Okay? In the second example, we're doing a natural log problem here. So remember, this is base e. We're assuming there's an e in here. We don't write log base e of x minus 4. By using the natural log notation, we know that we're taking log base e. So if I want to switch my x and y around, this becomes x equals the natural log of y take away 4. Again, keep in mind my base is e, so I want to write it in exponential form. This becomes e to the x power is equal to y take away 4. Well, now to solve that for y, we just add 4 to both sides, and I get y is equal to e to the x power plus 4. So the inverse of that function is y equals e to the x plus 4. Why don't you guys try a couple here and see what we can come up with. All right, let's get back at it here. Again, because this base here is 10, well, I don't know how many times I'm going to do that to you today. Sorry about that jumpiness of that video there. Since the base here is 10 and the base here is 10, 10 to the log base 10 of 7x is simply 7x. Simplifying this becomes 3 to what power is equal 27 to the x power. All right, so we need to write 27 as a power of 3. 27 is the same thing as 3 cubed, then to the x power. So this becomes 3 to the 3x power, because 3 times x is 3x. So 3 to what power equals 3 to the 3x power? Well, for obvious reasons, this is now 3x because these have to match. All right, let's take a look at an inverse function here. An inverse function now, when my base is 7, all right? And so what I want to do with this now is I want to interchange my x and y. So first of all, this is x equals 7 to the 2y power. All right? Now, my notation, remember, when I go to find the inverse, we just switched around the x and the y. And to put this in logarithmic notation, my base is 7. So this is log base 7. And again, it's 7 to the x power equals 2y. And so this becomes log base 7 of x is equal to 2y. Now to solve this function for y, to make it say y equals, we simply divide both sides by 2. And you get y is equal to log base 7 of x, the whole thing, divided by 2. All right? In our last example, again, we're going to switch around x and y. And we're going to solve this. We're going to write this in exponent notation. My base is e. Whenever we see natural log, my base is e. So it's e to the x is equal to y plus 6. Take away 6 from both sides. You get y equals e to the x power, take away 6. Now, I want you to take note of the fact that when we took the inverse of this with a base of 7, we ended up with log base 7. When we took the inverse of a natural log function whose base is e, we ended up with a base of e. All right? Now, we're going to take a little look at this idea of logarithmic functions and their graphs. Logarithmic functions and their graphs are very confusing in that we've never done them before. But if you think about the inverse, how the inverse of an exponential graph, for example, y equals ab to the x, is a logarithmic function. And if I just say y equals b to the x, the inverse of that would be log base b of x is equal to y. And so this logarithmic graph, y equals log base b of x, is the inverse of the function y equals b to the x. And so those two functions, because they're inverses, will be reflected across the line y equal x. If at exponential growth, the logarithmic function will look something like this because it has to mirror on the other side of the line y equal x. If it's exponential decay, then the logarithmic graph is going to be exponential. It's going to mirror that exponential decay. The big thing here, though, is keeping in mind that for the exponential growth, we got an asymptote at y equals 0. All right? And so because of that, when I take the inverse, I'm going to get an asymptote at x equals 0. Same thing over here. Because we get an asymptote at y equals 0, I'm going to get an asymptote here for my second function at x equals 0. All right, so that's kind of a big deal, and we'll kind of talk about that a little bit more as we go. First of all, the graph of y equals log base b of x is shown below. So that's this guy over here on the left-hand side, where b is greater than 1, or on the other side, on the right-hand side over here, where b is between 0 and 1. So this would be an exponential decay situation, and this would be a growth situation when I'm looking at the original exponential function. All right, and so obviously the inverse of that would be a logarithmic function as well. All right, because y equals log base b of x and y equals b to the x are inverse functions, like we just talked about, they're inverse functions. The graph of y equals log base b of x is the reflection of the graph y equals b to the x in the line y equal x. We're reflecting across that line y equals x. All right. Note that the y-axis is a vertical asymptote of the graph, of the logarithmic graph, and so the domain of the function is x has to be all numbers that are greater than 0. And again, what did we talk about? We said because this function was restricted to all values of y greater than 0, when I take the inverse of it, the values of x are only those numbers this way. Notice that my logarithm graph doesn't exist over here in the second and third quadrant. Same thing here. Here's my logarithmic graph. Notice that it kind of gets to an asymptote here at y, the vertical line, x equals 0. And so again, this part of the graph doesn't exist for the logarithmic graph. And so again, the domain of the logarithmic graphs is x has to be positive. All right. Now, the range is all real numbers, because in this case, as you pick values of x that are close to 0, you get close to negative infinity. And eventually, even though this is going very slowly, this will get up to positive infinity for the function. Same thing here. We're going to start with very high values, and we'll end up at, again, negative infinity going the other way. All right, so let's take a look at a couple of graphs. We don't have a good way to do this, unfortunately. We can't plug this into our graphing calculator and take a peek at this. So the best way to do this is to kind of use our definition of what a logarithmic function is and see if we can pick some convenient points. And they use this idea of convenient points, and I'll help you out a little bit with that as we go. All right, so let's start with the first one here. It says plot several convenient points such as 1, 2, and 4. Now, where are they getting those values? Because we know that 2 to the y power is equal to x. So 2 to the y is equal to x. And so we want to know 2 to what power is equal to 1? Well, we know anything to the 0 power is equal to 1. 2 to what power is going to be equal to 2? Well, 2 to the first power is equal to 2, and so that's the point 2, 1. 2 to what power is equal to 4? And again, 2 to the second power is equal to 4. And again, realize that these are my y values when x is equal to 1, 2, and 4. And so x will be equal to 2. Now again, realize that we pick these numbers because these numbers, since my base is 2, I'm picking numbers like 2 to the 0, 2 to the first, and 2 to the second for my x values, because then I know I'm going to get good numbers, good pretty numbers for my y values. All right, so let's go ahead and plot those points. Here's the point 1, 0. Here's the point 2, 1. And here's the point 4, 2. And again, remember that the y-axis is a vertical asymptote of this graph. Okay? It's a vertical asymptote. And so my graph is going to really be on the right side of that line. So it's going to kind of come up here like this, cross through those points, and continue on to the right. All right? It says from left to right, draw your curve that starts just to the right of that y-axis and moves up and through the plotted points. And obviously, that's kind of the graph that we drew there. All right? Okay, let's take a look at our next one on the other side here. Now, we're looking at a base of 1/3. So 1/3 to the y power is equal to our values of x. Now, this is going to be a little bit trickier because now what we're going to say is we're going to say, look, this is 1/3 to what power is going to give me 1? 1/3 to what power is going to give me 3? And 1/3 to what power is going to give me 9? Now, once again, I'm choosing numbers that are multiples of 3 because I know that 1/3 obviously is a, if I flip that thing upside down, that's going to give me multiples of 3. So, again, anything to the 0 power is 1, so that one's pretty easy. That's the point 1, 0. All right? Now, this next one's a little trickier because I want to know what power do I raise 1/3 to get 3? Well, I'm going to have to raise that to a -1 power because that helps me to flip 1/3 over and make it 3 over 1. And so when x equals 3, y equals -1 because 1/3 to the -1 power gives me 3. And the same is true for 1/3 to the -2 because 1/3 to the -2 flips upside down and becomes 3 over 1 to the +2, and 3 squared is 9. Once again, the y-axis is a vertical asymptote. And so let's plot our values. Now again, your x-axis here is counting by 2's. So the point 1, 0 is right there. The point 3, -1 is there's 2, 3, -1 is down here because this is counting by 1, 2, 3, etc., right? So that one's okay. And the point 9, -2, so there's 2, 4, 6, 8, 10, so right about there. And then down 2 is going to be somewhere in there. Now this guy's going to look a little crazier because in this case, now my vertical asymptote is here, right? So that means my graph is going to approach that. As you can see, as I'm moving from left to right, my graph is going down, isn't it? And so now I'm going to take this guy and I'm going to extend that graph. Oops, my hand's in the way. Sorry about that. There we go. So we'll get something like this. Again, from left to right, draw a curve that starts just to the right of the x-axis. and moves down through the plotted points. Again, keep in mind here that the base of this one was 2, and so the graph will be the graph of log base 2 will be an inverse of an exponential growth graph. An exponential growth graph will look something like this, right? And so that will be mirrored here. In the second example, y equal x is this line, so if I want to mirror this function, now I'm going to get an exponential decay graph. It's going to look something like this. All right, and obviously that's a little bit harder to see that they mirror, but that's the general idea. All right. So let's talk about this idea of h and k again. My goodness, you guys are getting tired of h and k, but h and k do some different things to my graph, right? In this case, because this is -1, I promise I won't do it again. This is -1, so this is going to move the graph to the right, 1, and the +2 is going to move it up 2. The question is from where? So let's start with the parent first. Let's start with y equals log base 3 of x, which really says 3 to the y power is equal to x. Well, I'm going to pick values of x like 1, 3, and 9 because those are multiples of 3. And so 3 to the 0 power is going to be equal to 1. And so again, my y value, this should be the point 1, 0, because 3 to the first power is equal to, 3 to the 0 power is equal to 1. So I'm saying what value of y is going to make this thing equal to 1? What value of y is going to make this thing equal to 3? Well, 3 to what power is going to give me 3? Well, that's got to be to the first power, and so this is 3, 1. And then finally, 3 to what power is going to give me 9? So that becomes a 2. Let's go ahead and plot those points. I'll do those ones in blue. So that's the point 1, 0, which is like right in there. The point 3, 1, which is right in there. And the point 9, 2. 2, 4, 6, 8, 10. Over back here is 9. And then 1, 2 is like right in there. Again, this is an exponential. This is the inverse of an exponential growth function. And so it's going to mirror an exponential growth. We have a vertical asymptote here. And so let's take a look at the parent graph first. Here's the parent graph. Okay, that is log base 3 of just x all by itself. All right, now let's switch pen colors here. And let's translate all of those points, right 1 and up 2. So we're going to go right 1 and up 2. We are going to go right 1 and up 2. We are going to go right 1 and up 2. And so my new graph is going to look something like this. Now, the asymptote is much harder to see, but we're going to translate the parent graph right by 1 unit and up by 2 units. The translated graph will then pass to the point, where are my numbers here? This takes the point 1, 0 and moves it over 1 and up 2, so that would be the point 2, 2. All right. The next will be 4, 3, and the last will be 10, 4, because again, we moved it right 1 and up 2. Now the graph's asymptote, because we moved it to the right by 1, remember we had a vertical asymptote at x equals 0. So because I moved it right 1, I'm going to also move the asymptote to the right 1. And so now my new vertical asymptote will be at x equals positive 1, because again, we basically slid the whole graph to the right by 1 unit. The domain of the function is x has to be greater than 1, again, not equal to, because it'll never actually get to x equal 1. And the range is all real numbers. All right, why don't you guys try the last checkpoint problem on your own here. We'll be right back with a solution for you. All right, here it is. So we want to first think about the parent graph, y equals log base 1/2 of x. All right, and so to graph the original function, again, because this base is 1/2, this is going to be the inverse of an exponential decay graph, but I'm going to get a couple of values here for my x and my y. We want to choose numbers that have powers that are related to 1/2, so numbers like 1, 2, 4, and 8, things like that. And so now what we're going to do is we're going to write this in exponential form. So this is 1/2 to the y power is equal to x. So 1/2 to what power gives me 1? Well, 1/2 to the 0 is 1, because anything to the 0 power is 1. All right? 1/2 to what power gives me x, which is now 2. Well, 1/2 to what power gives me a 2? I have to take this guy and flip it upside down, so that means it's -1. So 1/2 to the negative 1 power is going to give me 2. How about 1/2 to the negative, first of all, 1/2 to the negative what is going to give me 4? Well, it's got to be negative because it's got to flip it upside down, and then 2 squared is going to give me 4, so this has to be -2, and just so you know, this will also be -3. All right? And so we're going to go ahead and plot those points. Here's the point 1, 0. Here's the point 2, -1. Here's the point 4, -2. And the point 1, 2, 3, 4, 5, 6, 7, 8, -1, 2, and 3. Probably right in there someplace. And again, we're going to have a vertical asymptote at the line x equals 0. And so my graph is going to look something like this. And going to continue on down like this. All right? That's the original parent function. Now, what is the -3 going to do to this thing? Well, my -3 is going to take this whole graph and shift it down by 3 units. There's nothing affecting the x left or right because, again, it's not log base 1/2 of x minus 3 like this. So if it were like this, it would translate it to the right by 3 units. But because there are no parentheses, now it's just going to move it down 3. So take each of these points and go 1, 2, 3 down, 1, 2, 3 down, 1, 2, 3 down. And again, this guy would be like 1, 2, 3 down here. And so my new graph, now because we haven't shifted the asymptote left to right, we haven't moved this graph left to right at all, my asymptote is still going to be right here at x equals 0. But the graph that's connecting these points, sorry, I'm having a hard time getting my pen to behave here. The graph that's connecting these points is going to look something like this. So once again, you're going to have a vertical asymptote at x equals 0. So the domain for this is x is greater than 0, not greater than or equal to, because x is never equal to the asymptote. And the range is all real numbers. I'll say range and domain. All right? And so that concludes our lesson on logarithmic functions.